going to use exactly the same reaction, but I'm going to do a different thing with it. Okay? A lot of people will look at this reaction and say, well, it's hydrochloric acid and it's calcium carbonate. Hydrochloric acid is an acid. Acids have pH. If you react the acid, then the pH should go up. I can measure pH and get a reaction rate. Okay? And it seems very straightforward. But what I want to show you is that using pH to measure reaction rate, it's not as straightforward as you would think. At the same time that I'm using pH, I'm also going to be using temperature. All right, so we're going to map those two things. Temperature and pH. Now, obviously, if you were going to do what's called a thermometric titration or a thermometric reaction, you would have insulation around the thing and you would have a cap on it and all that kind of stuff. This is a completely open system, so it's not going to be very accurate. But that's okay. It's just a demonstration. All right. Now, if you do decide to use pH, you can do it, okay? You can manipulate things to make it work correctly. I'm not saying that you can't. I am saying that it's a little difficult. All right. I'm breaking my own rule here. My rule is that when you take this little thing off, you need to put it into a very small beaker so that you don't tip it over. I'm breaking my own rule, and watch me accidentally tip it over and blow stuff out. pH probes are very delicate. You have to keep them wet. Potassium chloride solution there. I'm rinsing it off with water. They have to remain wet. If they dry out, they no longer work. Then I drop it into the solution. I've got my thermometer here. These thermometers are tough, so you can actually use them to stir things if you wish, and that's fine. The glass thermometers, you can't do that. Fire up Data Studio again, because I've changed probes. And it will give me that string. Now, I'm not interested in all of that stuff. I am interested in graphs, though. I can choose what I want. I want temperature, graph, and I also want pH, graph. And I can pull them apart so that I can see them one below the other and how they change with each other. Now, theoretically, temperature will be going up because reaction releases heat, and pH will be going up because acids are very low in pH. If I react the acid away, then the pH will rise. Okay? Theoretically. Let's see what happens. Now, as usual, I will start so that we have a baseline. Notice we already have a little bit of a problem. We're reading negative pH, which is theoretically impossible, but that's because I haven't calibrated this thing. All right. I'm going to take some marble chips, dump in there, and stir. Oh, that's working a lot better than that. All right. We'll let it go for a little bit. Okay, now there's been so many bubbles being produced, it's pretty much stirring itself, so I'm just going to let it do it. This is one of the problems with using pH. I'll explain how pH is measured in a moment. Okay, so voltage I'm not interested in. Absolute pressure I'm not interested in. And so you can see that the temperature doesn't look like it's rising very much. Doesn't surprise me too much because it's not an insulated container. But again, it's taking measurements at much more precision than it's reading out there. So let's let it run for about 30 more seconds. How about that? All right. Now, if we look at the first graph and blow it up, scale to fit, then you get more than what you thought, okay? You do get a steady temperature rise. Now this looks a lot more similar to a graph that you see in a book, because the graph that you see in a book is a curve that goes up and tends to begin to flatten out after a while. Now the best place to measure the rate for a reaction is right there at the beginning of that curve, because that's the rate when you know what the concentration is. Because as that reaction goes on, the concentration of acid gets less and less and less and less and less. And the only time that you know that that acid is 1 mole per decimeter cubed is right there at the beginning. Okay? It's the only time. Over here, I don't know what the concentration is. And we'll be doing that. It's called the method of initial rate. Now let's look at pH. For a while there, it looked like it was doing pretty much what we thought it should do, right? pH was rising. Then it hit a plateau at -1, which is already theoretically impossible, and then begins to go down. Okay? Now the reason for that is that the pH probe has a glass vial in it, and what it's actually measuring is ions moving back and forth across that glass. And as those ions go, it gives it an electrical current, and it's measuring that current directly. So anything that messes with that current messes with the pH reading. Well, one thing that messes with the current, of course, is bubbles, because the bubbles are gas, and the pH probe is designed to work purely in a liquid. So the fact that I've used calcium carbonate to produce carbon dioxide means that my pH probe is going to give me anomalous readings. Plus the fact that a 1-digit change in pH is a 10 times change in hydrogen ions. Makes it difficult to use pH. So unless you're just really bent on using pH, I would recommend that you don't, actually. Okay? And I just wanted to show you that so that you would believe me when I tell you it usually doesn't